All right, recording is rolling. Welcome to Wednesday, December 8th. So today I'm gonna have you guys finish this lab that you were doing yesterday, but gonna take the first few minutes of class to remind you guys how this works, give you guys some insight as to what the answer should be. So you guys had this set up, this PVC pipe that was shaped like a T, and it's spinning about this vertical central axis. You're trying to figure out what is the rotational inertia associated with that. So, say if you put a torque on it, it'll cause it to spin, but the more rotational inertia, the less it will accelerate spinning, angular acceleration. So, what is the value of that angular acceleration? So, let me show you guys an alternate way that you could solve this. That's what's going on right here. You guys remember in your textbook on page 206, is this table of rotational inertia values for some common shapes. And one of them actually looks a lot like your guys' lab. This is a horizontal pipe spinning about this central axis here, about its center. And that is 1/12 ml squared. That should be able to model pretty close the answer to this lab. So if you did, I measured this morning, what is the mass of one of these arms? It's 152 grams. That's 0.152 kilograms. Double that to get the total mass. Here's 1/12 ml squared. So there's the mass of that whole crossbar T. Now I'm ignoring the vertical pipe because even though it has mass, it doesn't have hardly any radial distance. So it probably adds negligibly to the rotational inertia. So just focus on that crossbar. Okay. And then the full length of this was 1.25 meters. So pop that in, 112 times the total mass of 1.25 meters squared. I got this for the rotational inertia, 0.04 kilogram meter squared. Now, this is one approach. You guys are doing a more empirical approach, going through torque and angular acceleration, but your answer should be kind of in this ballpark. It should be pretty close to this. You might get 0.05 or 0.1 or 0.02, but it should be like somewhere pretty close to that. So let's look at this whole thing like backwards in order, because I showed you guys yesterday how to do this from beginning to end, but how would I know to, say, design a table a certain way to lead there? Well, let's work back from the answer. So the very last thing you guys are going to do is make a graph, torque versus angular acceleration. And the reason you're going to do that is because the slope of that line, and these points should line up in a straight line, is the answer to this lab because of this formula right here. Torque equals rotational inertia times angular acceleration. Remember, this is analogous to F equals ma. Okay? I did mention, too, that there should be a y-intercept here. You might not get one. Maybe you get your data and actually does go through origin, but I'm pretty sure you will get a y-intercept. Did any of you guys figure out between yesterday and today, now that you've been thinking about this for about a day, what that would represent? Like, why would there be a y-intercept? Not a critical thinking question, right? So you guys know this is the point 0, 0. So at 0 radians per second squared, like if there's no angular acceleration at all, well, there would be, some initial torque associated with that. Maybe think of it kind of like this. What if you pick one of the tiny lab weights, like this little tiny one right here, and you hang this from this rig, right? And maybe it just hangs at rest and doesn't even move. Kind of like, hey, like equilibrium, right? And why would that happen? Well, maybe because there was some friction to start with, and there is. I mean, there's like plastic parts that are rubbing against each other, so there's some friction associated with that. This intercept, tau naught, represents the frictional torque. That's what that would be, and it only starts rotating like beyond that. So that's what that would be. So maybe I have to modify tau equals I alpha and say this is tau net, kind of like net force equals mass times acceleration. Okay? And then, okay, that would be the difference between torque and the frictional torque. And then, hey, this looks like y equals mx plus b, doesn't it? Okay. So that should be what your graph looks like and how this ends up. Now, how do you get torque and how do you get alpha? Remind you guys where this comes from. So here's the graph space. Here's the answer to the lab. All right, let's look at this table real fast, backwards in order. Okay. So torque is going to come from R cross F. Now, you know the radial size of that pipe, remember, is about 1.1 centimeters radius central pipe, times the tension of the string is actually providing the force. Because you guys remember, if you zoom in, right, the tension of the string is providing force that's causing a torque about R cross F. Okay. But where do you get that tension? It should be pretty close to the lab weight, but it should actually be a little bit less. Well, that's where you set up a free body diagram, like I showed you guys at the beginning of the class yesterday, and it works out to be, So sorry guys, let me the wrong button there. Mass times gravity field minus the acceleration of the lab weight. That's what the tension would end up working out to. But what is the acceleration? Okay. Well, that depends on drop distance and the time of that drop distance. So that goes back to that college equation, x equals 1/2 at squared, but you solve for a, you get 2x over t squared. So, and here's where we're getting into direct measurements finally. Drop distance x, drop time t, and then, okay, right, now you can at least get all the way to torque. Also measure, of course, the radial size of the pipe. Okay. The other thing you need to know to plot points on this graph, like coordinates, is alpha, the angular acceleration. So that comes from that linear acceleration that I just reminded you guys how to solve using the college equation, divided by the radial size of the pipe, and you would have those numbers also by that point. Okay, so got some direct measurements. You guys got some calculations you can do, so you can plot points on this graph. You know what this graph should look like. I think yesterday you guys probably did 2 or 3 rows. So today you guys got the rest of class to finish getting data, make this graph, get this answer. One more detail I want to mention while you guys are here is look at the midterm schedule real fast. Tomorrow I'll start the midterm review. You guys will take a few days to do midterm review. It's going to be multiple choice, and there's going to be a couple of free response type questions I'll have for you guys too. But I'll give you guys a really comprehensive review over the next few days to make sure I hit everything for you guys. Let's see. The very first exam is going to be next Thursday, and that'll be your 7th period exam. That'll be on December 16th. I'm not actually going to be at the school myself on that day because I have jury duty. Here's my jury summons. Just so you know, hopefully this is just a one-day thing, but who's to say? But just so you know, in case you don't see me on campus, that'll be fine. All right, so you guys got rest of class. Just turn this lab into the gray tray before you take off. Okay.